The next thing that I hope is very clear is that the elements across the batch dimension, which are independent examples, never talk to each other. They're always processed independently. And this is a batched matrix multiply that applies basically a matrix multiplication kind of in parallel across the batch dimension. So maybe it would be more accurate to say that in this analogy of a directed graph, we really have, because the batch size is 4, we really have 4 separate pools of 8 nodes, and those 8 nodes only talk to each other. But in total, there's like 32 nodes that are being processed. But there's sort of 4 separate pools of 8. You can look at it that way. The next note is that here in the case of language modeling, we have this specific structure of directed graph where the future tokens will not communicate to the past tokens. But this doesn't necessarily have to be the constraint in the general case. And in fact, in many cases, you may want to have all of the nodes talk to each other fully. So as an example, if you're doing sentiment analysis or something like that with a transformer, you might have a number of tokens, and you may want to have them all talk to each other fully, because later you are predicting, for example, the sentiment of the sentence. And so it's okay for these nodes to talk to each other. And so in those cases, you will use an encoder block of self-attention. And all it means that it's an encoder block is that you will delete this line of code, allowing all the nodes to completely talk to each other. What we're implementing here is sometimes called a decoder block. And it's called a decoder because it is sort of like decoding language. And it's got this autoregressive format where you have to mask with the triangular matrix so that nodes from the future never talk to the past, because they would give away the answer. And so basically in encoder blocks, you would delete this, allow all the nodes to talk. In decoder blocks, this will always be present so that you have this triangular structure. But both are allowed, and attention doesn't care. Attention supports arbitrary connectivity between nodes. The next thing I wanted to comment on is you keep hearing me say attention, self-attention, etc. There's actually also something called cross-attention. What is the difference? So basically, the reason this attention is self-attention is because the keys, queries, and the values are all coming from the same source, from X. So the same source X produces keys, queries, and values. So these nodes are self-attending. But in principle, attention is much more general than that. So for example, in encoder-decoder transformers, you can have a case where the queries are produced from X, but the keys and the values come from a whole separate external source, and sometimes from encoder blocks that encode some context that we'd like to condition on. And so the keys and the values will actually come from a whole separate source. Those are nodes on the side, and here we're just producing queries, and we're reading off information from the side. So cross-attention is used when there's a separate source of nodes we'd like to pull information from into our nodes. And it's self-attention if we just have nodes that would like to look at each other and talk to each other. So this attention here happens to be self-attention. But in principle, attention is a lot more general. Okay, and the last note at this stage is, if we come to the attention is all you need paper here, we've already implemented attention. So given query, key, and value, we've multiplied the query and the key, we've softmaxed it, and then we are aggregating the values. There's one more thing that we're missing here, which is the dividing by 1/square root of the head size. The dk here is the head size. Why are they doing this? Why is this important? So they call it the scaled attention. And it's kind of like an important normalization to basically have. The problem is if you have unit Gaussian inputs, so zero mean, unit variance, k and q are unit Gaussian, then if you just do way naively, then you see that your way actually will be, the variance will be on the order of head size, which in our case is 16. But if you multiply by 1/head size square root, so this is square root and this is 1/, then the variance of way will be 1, so it will be preserved. Now, why is this important? You'll notice that way here will feed into softmax. And so it's really important, especially at initialization, that way be fairly diffuse. So in our case here, we sort of locked out here, and way had a fairly diffuse numbers here. So like this. Now the problem is that because of softmax, if way takes on very positive and very negative numbers inside it, softmax will actually converge towards one-hot vectors. And so I can illustrate that here. Say we are applying softmax to a tensor of values that are very close to 0, then we're going to get a diffuse thing out of softmax. But the moment I take the exact same thing and I start sharpening it, and making it bigger by multiplying these numbers by 8, for example, you'll see that the softmax will start to sharpen. And in fact, it will sharpen towards the max. So it will sharpen towards whatever number here is the highest. And so basically, we don't want these values to be too extreme, especially at initialization. Otherwise, softmax will be way too peaky. And you're basically aggregating information from like a single node. Every node just aggregates information from a single other node. That's not what we want, especially at initialization. And so the scaling is used just to control the variance at initialization. Okay, so having said all that, let's now take our self-attention knowledge and let's take it for a spin. So here in the code, I've created this head module and it implements a single head of self-attention. So you give it a head size, and then here it creates the key, query, and the value linear layers. Typically, people don't use biases in these. So those are the linear projections that we're going to apply to all of our nodes. Now here, I'm creating this trill variable. Trill is not a parameter of the module. So in sort of PyTorch naming conventions, this is called a buffer. It's not a parameter. And you have to call it, you have to assign it to the module using a register buffer. So that creates the trill, the lower triangular matrix. And when we're given the input x, this should look very familiar now. We calculate the keys, the queries, we calculate the attention scores inside way. We normalize it, so we're using scaled attention here. Then we make sure that future doesn't communicate with the past, so this makes it a decoder block. And then softmax, and then aggregate the value and output. Then here in the language model, I'm creating a head in the constructor, and I'm calling it self-attention head. And the head size I'm going to keep as the same and embed, just for now. And then here, once we've encoded the information with the token embeddings and the position embeddings, we're simply going to feed it into the self-attention head, and then the output of that is going to go into the decoder language modeling head and create the logits. So this is sort of the simplest way to plug in a self-attention component into our network right now. I had to make one more change, which is that here in the generate, we have to make sure that our IDX that we feed into the model, because now we're using positional embeddings, we can never have more than block size coming in, because if IDX is more than block size, then our position embedding table is going to run out of scope because it only has embeddings for up to block size. And so therefore I added some code here to crop the context that we're going to feed into self, so that we never pass in more than block size elements. So those are the changes, and let's now train the network. Okay, so I also came up to the script here and I decreased the learning rate because the self-attention can't tolerate very, very high learning rates. And then I also increased the number of iterations because the learning rate is lower. And then I trained it, and previously we were only able to get to up to 2.5, and now we are down to 2.4. So we definitely see a little bit of an improvement from 2.5 to 2.4 roughly, but the text is still not amazing. So clearly the self-attention head is doing some useful communication, but we still have a long way to go. Okay, so now we've implemented the scale.product attention. Now next up in the attention is all you need paper. There's something called multi-head attention. And what is multi-head attention? It's just applying multiple attentions in parallel and concatenating the results. So they have a little bit of diagram here. I don't know if this is super clear. It's really just multiple attentions in parallel. So let's implement that. Fairly straightforward. If we want a multi-head attention, then we want multiple heads of self-attention running in parallel. So in PyTorch, we can do this by simply creating multiple heads. So however many heads you want, and then what is the head size of each. And then we run all of them in parallel into a list and simply concatenate all of the outputs. And we're concatenating over the channel dimension. So the way this looks now is we don't have just a single attention that has a hit size of 32, because remember, an embed is 32. Instead of having one communication channel, we now have 4 communication channels in parallel. And each one of these communication channels typically will be smaller correspondingly. So because we have 4 communication channels, we want 8-dimensional self-attention. And so from each communication channel, we're getting together 8-dimensional vectors, and then we have 4 of them, and that concatenates to give us 32, which is the original and embed. And so this is kind of similar to, if you're familiar with convolutions, this is kind of like a group convolution, because basically instead of having one large convolution, we do convolution in groups, and that's multi-headed self-attention. And so then here we just use SA heads, self-attention heads instead. Now I actually ran it, and scrolling down, I ran the same thing, and then we now get this down to 2.28 roughly. And the output is still, the generation is still not amazing, but clearly the validation loss is improving because we were at 2.4 just now. And so it helps to have multiple communication channels because obviously these tokens have a lot to talk about. They want to find the consonants, the vowels, they want to find the vowels just from certain positions. They want to find any kinds of different things. And so it helps to create multiple independent channels of communication, gather lots of different types of data, and then decode the output. Now, going back to the paper for a second, of course, I didn't explain this figure in full detail, but we are starting to see some components of what we've already implemented. We have the positional encodings, the token encodings that add. We have the masked multi-headed attention implemented. Now, here's another multi-headed attention, which is a cross attention to an encoder, which we're not going to implement in this case. I'm going to come back to that later. But I want you to notice that there's a feed-forward part here, and then this is grouped into a block that gets repeated again and again. Now, the feed-forward part here is just a simple multi-layer perceptron. So the multi-headed, so here position-wise feed-forward networks is just a simple little MLP. So I want to start basically in a similar fashion, also adding computation into the network. And this computation is on a per-node level. So I've already implemented it, and you can see the diff highlighted on the left here when I've added or changed things. Now, before we had the multi-headed self-attention that did the communication, but we went way too fast to calculate the logits. So the tokens looked at each other, but didn't really have a lot of time to think on what they found from the other tokens. And so what I've implemented here is a little feed-forward single layer. And this little layer is just a linear followed by a ReLU nonlinearity, and that's it. So it's just a little layer, and then I call it feed forward and embed. And then this feed forward is just called sequentially right after the self-attention. So we self-attend, then we feed forward. And you'll notice that the feed forward here, when it's applying linear, this is on a per token level. All the tokens do this independently. So the self-attention is the communication, and then once they've gathered all the data, now they need to think on that data individually. And so that's what feed forward is doing. And that's why I've added it here. Now, when I train this, the validation loss actually continues to go down, now to 2.24, which is down from 2.28. The outputs still look kind of terrible, but at least we've improved the situation. And so as a preview, we're going to now start to intersperse the communication with the computation. And that's also what the transformer does when it has blocks that communicate and then compute, and it groups them and replicates them. Okay, so let me show you what we'd like to do. We'd like to do something like this. We have a block, and this block is basically this part here, except for the cross attention. Now the block basically intersperses communication and then computation. The communication is done using multi-headed self-attention, and then the computation is done using a feed-forward network on all the tokens independently. Now, what I've added here also is, you'll notice, this takes the number of embeddings in the embedding dimension and the number of heads that we would like, which is kind of like group size in group convolution. And I'm saying that the number of heads we'd like is 4. And so because this is 32, we calculate that because this is 32, the number of heads should be 4. The head size should be 8, so that everything sort of works out channel-wise. So this is how the transformer structures sort of the sizes, typically. So the head size will become 8, and then this is how we want to intersperse them. And then here, I'm trying to create blocks, which is just a sequential application of block, 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 so that we're interspersing communication feed-forward many, many times, and then finally we decode. Now, I actually tried to run this, and the problem is this doesn't actually give a very good answer, and a very good result. And the reason for that is we're starting to actually get like a pretty deep neural net. And deep neural nets suffer from optimization issues, and I think that's what we're kind of like slightly starting to run into. So we need one more idea that we can borrow from the transformer paper to resolve those difficulties. Now, there are two optimizations that dramatically help with the depth of these networks and make sure that the networks remain optimizable. Let's talk about the first one. The first one in this diagram is, you see this arrow here? and then this arrow and this arrow, those are skip connections, or sometimes called residual connections. They come from this paper, Deep Residual Learning for Image Recognition, from about 2015, that introduced the concept. Now, these are basically, what it means is you transform the data, but then you have a skip connection with addition from the previous features. Now, the way I like to visualize it, that I prefer, is the following. Here the computation happens from the top to bottom, and basically you have this residual pathway, and you are free to fork off from the residual pathway, perform some computation, and then project back to the residual pathway via addition. And so you go from the inputs to the targets only via plus and plus and plus. And the reason this is useful is because during backpropagation, remember from our micrograd video earlier, addition distributes gradients equally to both of its branches that fed as the input. And so the supervision, or the gradients from the loss, basically hop through every addition node all the way to the input, and then also fork off into the residual blocks. But basically you have this gradient superhighway that goes directly from the supervision all the way to the input, unimpeded. And then these residual blocks are usually initialized in the beginning, so they contribute very, very little, if anything, to the residual pathway. They are initialized that way. So in the beginning, they are sort of almost kind of like not there. But then during the optimization, they come online over time, and they start to contribute. But at least at the initialization, you can go from directly supervision to the input. Gradient is unimpeded and just flows, and then the blocks over time kick in. And so that dramatically helps with the optimization. So let's implement this. So coming back to our block here, basically what we want to do is we want to do x equals x plus self-attention and x equals x plus self.feedforward. So this is x, and then we fork off and do some communication and come back. And we fork off and we do some computation and come back. So those are residual connections. And then swinging back up here, we also have to introduce this projection. So nn.linear, and this is going to be from after we concatenate this. This is the size n embed. So this is the output of the self-attention itself, but then we actually want the to apply the projection, and that's the result. So the projection is just a linear transformation of the outcome of this layer. So that's the projection back into the residual pathway. And then here in the feed forward, it's going to be the same thing. I could have a self.projection here as well, but let me just simplify it, and let me couple it inside the same sequential container. And so this is the projection layer going back into the residual pathway. And so that's, well, that's it. So now we can train this. So I implemented one more small change. When you look into the paper again, you see that the dimensionality of input and output is 512 for them. And they're saying that the inner layer here in the feed forward has dimensionality of 2048. So there's a multiplier of 4. And so the inner layer of the feed forward network should be multiplied by 4 in terms of channel sizes. So I came here and I multiplied 4 times embed here for the feed forward, and then from 4 times n embed coming back down to n embed when we go back to the projection. So adding a bit of computation here and growing that layer that is in the residual block on the side of the residual pathway. And then I trained this, and we actually get down all the way to 2.08 validation loss. And we also see that the network is starting to get big enough that our train loss is getting ahead of validation loss. So we start to see like a little bit of overfitting. And our generations here are still not amazing, but at least you see that we can see like is here, this now, grieve sync. Like this starts to almost look like English. So yeah, we're starting to really get there.